Okay, so hello everybody. I'm Lara from Eprosima, and today I'm going to host this embedded working group. For the people who has joined recently, in the document I'm sharing, please write your name on the attending list. And also you can add some topics to the miscellaneous section, some topics that you want to discuss later. And okay, as a recap, let's have a look at the last agenda of the embedded working group, of the last embedded working group. And we had here Jan Stasiuslat from BOSS, and we had a discussion about advanced execution concepts in micro-ROS. Bartolomé Jiménez also talked about micro-ROS at Capra Robotics. And then Tanmay Deshmukh from Colescent Mobile Robotics talked about retail automation. And for today's meeting, we have the notorious collaboration of Daniel Mesham from Auterion, who will talk about the bridge between micro-ROS and PX4 with micro-XRCE-DDS. And also he will show an amazing demonstration. And Tom Nilson from Mezli will be here too, and we'll discuss about Mezli, the company behind the first restaurant that works completely autonomously. So, Daniel, if you want to begin, is your turn.
Sorry, was it me or Tom first?
I think it's you.
Happy to go. Yep.
Oh no, okay.
Well, as you wish.
I was wrong. For me, it's the same.
No preference on my end either.
Okay, go,
Okay.
Daniel.
Alrighty. Then let me share my screen. One moment. There we go. I think we're good to go. All right. Great. Thanks, everyone. Thanks for the introduction, Lara. So my name is Daniel Mesham, and I'm working at Auterion, specifically involved in robotics and the software surrounding that. And as the title suggests, today I'm going to have a quick chat about how we at Auterion are making this move towards bridging PX4 with ROS2 using micro-XRCE-DDS. So to give a brief outline of what I'll go through today, first of all, I'll just give a bit of a background to Auterion, what we do and what our objectives are on a very high level. And then from there, we'll have a look at the design of the system that we're working on, its current design, and then at a new target design that we want to work towards, and what our objectives are with that. And this starts to play into why we need to consider micro-XRCE-DDS. And so finally, I'll then look specifically at micro-XRCE-DDS, where it fits into our changes, the current state of the work we're doing, and then present an initial example of what we've been working on so far. So first up, a bit about us, Auterion. So Auterion, our business is drones, and the best way to describe what we do is we provide and develop the single software platform or software ecosystem that can run on many drones and enable you to fly and use a variety of vehicles. One of the best ways I find to think about this is to say Auterion is to drones and autonomous vehicles what Android is to mobile phones. So it's one software platform, but it runs on multiple devices. Now, a key part of what we do is setting standards for autonomous vehicles, and we're a very involved company in the open source community. Indeed, we really grew up out of an open source project, specifically the PX4 autopilot software. And so a lot of the work we do actually ends up being open sourced, particularly within PX4. As a company, I think we are one of the top, if not the top contributors to PX4, and our individual developers consistently fill out most of the top 10 of the biggest contributors to the PX4 software. So we're really committed to these open source software stacks. And in doing so, we're trying to set the standards for not only drones, but autonomous vehicles in general, because so many more people are now using these software setups that we are contributing to. And it's not just the software that we're contributing to. We also have started to do some work on the hardware. So particularly, I would draw attention to our SkyNode, which is an embedded device which we use as a reference design for what your electronics should look like on a vehicle if you really want to make the most out of the Auterion ecosystem, and particularly the PX4 setup. And so this is one of our key hardware designs, which we really consider to be one of the standards that we encourage our operators and users to employ when they want to have a successful drone integration. So looking a bit more at the sort of business case, what do we really do? Auterion provides quite a lot in the range of what you really need to deploy and use drones for business uses. So of course, we've got the baseline platform, which has the PX4 application stack, so that runs the core flight control. We have our Auterion OS running, which has some more higher level functionalities, allows you to add in extra payloads such as cameras and things like that. And this all completes the package which would run on the SkyNode to enable you to fly the vehicle. Thanks for the question I see there. If it's okay, shall we take some questions all together at the end? If that's okay for everyone, and we can come back to you. Thanks. So that was the thing. That's the sort of core platform we've got there. On top of that, we have some additional core applications which are not necessarily on board the vehicle, but are still quite essential. So we have the Auterion suite, which is our cloud solution, which lets you analyze flights in the cloud after the fact, as well as Auterion mission control, which operators and pilots on the ground can use to control their vehicles. And finally, on top of all of that, you can have other onboard apps that you can really plug into the baseline platform to enable specific functionalities or use cases. And these are things that both we develop and our partners and other third parties can develop. And this enables you to really accelerate whatever business workflow you have using the Auterion ecosystem. Most of the work is done for you, and you can really focus on the end use and the final business use case to get the core data you need from the drone and not worry about how to fly the drone. Right, so I think that's enough about Auterion in general. Let's be a bit more specific about the system we're dealing with, and where micro-XRCE-DDS will come in. So first up in the system design section is, what is our current design, particularly in terms of how we've set up things on the SkyNode? So the SkyNode essentially has two onboard computers. The first is the microcontroller, or the flight control unit, or flight management unit, FMU, and the second is a mission computer. So first of all, looking at the microcontroller, this is what runs PX4, the software, and this is a fairly standard sort of a control architecture here. We have some estimators which collect the data, and they feed this to a commander, which then decides what to do with it. And what it really decides is, what is the high-level objective we want for our flight? And it does this by selecting a particular mode in the navigator. So this might be an automatic survey mode, or an orbit mode, or a simple hold position mode. This defines the high-level flight objective. So this data is then passed to the controllers, which define specific set points for the drone. And finally, we have allocation, where we define what each individual actuator must do. On the mission computer, what you can have is additional apps running with various extra sort of higher level functionality. And these would, in essence, take the place of some of the navigator modes. These would still collect data from the commander and send it back to the controllers. But as you can see, I've just indicated this with a bit of a gray arrow, because the way each of these apps do it is a little bit different each time. And there are a couple of ways that this is done, and it's never quite the same each time. Speaking of that, how we bridge these two is, well, there are two solutions we have at the moment. One is using Mezli, which is a protocol designed specifically to be used on these aerial vehicles. And the other is using micro-RTPS, which is something that is a bit of a precursor, actually, to micro-XRCE-DDS. Was built together with the PX4 team and the Proxima, and is now a sort of legacy solution that continues to be used in this PX4 use case. And so it's between one of these two, sometimes both. It's how data gets passed between these two onboard computers. Now, what you can see here is there's a bit of a mix across the two sides of some real-time operations, so operations that are real-time required. These need to run quickly to ensure safe flight, and some more non-critical things, which are more to do with the higher-level navigation logic, such as these navigator modes or these off-board apps. And so there's a bit of a mix, particularly on the microcontroller, of some real-time operations and some non-real-time operations. So this brings me now to discuss our target design, what we actually want to achieve. So in the target design, some of the things are the same, but what's different now is that we add in, or rather we split up the real-time required operations and the non-critical, non-real-time operations. So having a closer look here, what we envision is a flight controller within PX4 where we only keep sort of safety critical modes, or the very simple baseline flight modes on board, and these are now real-time required modes. Then we transfer anything that's non-critical that provides a higher level navigation logic. We transfer that to the mission computer, where it runs ideally within ROS2, maybe as individual nodes or multiple nodes altogether. And so we've split up these flight control modes. But in order to do that, we want to have some kind of single solution of how these communicate with the broader flight control architecture. And so we introduced this mode API, which allows the commander to say, I want to execute this mode, and it doesn't have to worry about whether it's a safety critical real-time mode or one of the higher level ROS2 modes. It doesn't need to know which device it's running on. Similarly, once one of these modes is decided on the high level objective, it needs to have a single point of contact with the controllers. And so we have this control API, which allows all these different modes, wherever they may be running, to interact with our onboard controllers. Now, once again, as on the previous slide, we need some kind of bridge between these two devices. And as you might have guessed it, this is where micro-XRCE-DDS comes into play. So what are the objectives that we want to achieve with this new target design that I've described briefly? And I think I have alluded to some of them. So are the high-level goals of making the split, of putting safety critical on one side and non-safety critical on the other side, is that it can allow us to have more complex navigation functionality. So if we've got these modes running in ROS, they can employ perhaps greater processing power of a more powerful mission computer and do more complex tasks that we may not be able to execute and run from a software point of view on the more limited microcontroller. At the same time, it allows us to keep the software on the microcontroller to be a very trusted, well-documented, well-tested, safety critical core to the whole ecosystem. So we know that if there's ever any issue on the mission computer, what's running on the microcontroller is really solid and we can rely on it. So what are the key requirements in order to achieve this? First of all, we need a robust commander, which can handle these different modes and fail safes and knows how to switch between them in various occasions. And then, of course, we need these well-defined mode and control APIs that I described earlier, where we interact with these modes in one of the two devices. And finally, as you might imagine, we need data transparency between the devices so that they can all work on the same data. And so finally, in order to achieve these requirements, what are the required functionalities? And particularly to do with the data transparency, we need state synchronization between devices. So if the data on one is the same as the data on the other, as well as message transparency between the devices. Meaning that when something is updated on one or data is sent out on one side, it's received on both sides and both get the same information at the same time. So as you can imagine, with all of this going on, the bridge between these two devices is crucial, because if the bridge is not working or if it's not enabling things fully, the two sides don't have the state synchronization and this message transparency that we really need. And so that brings us to why we need to add in micro-XRCE-DDS. So why did we go with micro-XRCE-DDS, I guess, and why do we see it as a very valuable tool in this case? And so the first thing to say is that it was designed for and around micro-ROS, which has many similarities to our use case here with PX4, and indeed, you can actually use micro-ROS in conjunction with PX4. We really like it because it is made for ROS, so it really has a kind of simple out-of-the-box usage, and it's widely understood by the robotics community in general because everyone is typically quite familiar with ROS. It also has improvements to the performance and functionality of the bridge. So it has a reduced memory and CPU footprint, which is critical compared to our previous implementation. It has a wider range of transport protocols and also more reliability profiles. So it really enables us to customize our use even more. And finally, as I said, Auterion really likes open source. And so micro-XRCE-DDS really fits in with our philosophy because it comes from the open source community as well. It has the same broad developer base. And crucially, it's maintained by the experts, not in flight control, but rather in middleware. And this is where it really has an advantage over our existing bridge, because that was being maintained by flight control people and not necessarily middleware people. And so this is why we are quite keen on micro-XRCE-DDS. So what's the current state of our integration and making this change from our old system design to the newer one that I described? Well, the first big step was that micro-XRCE-DDS has now been made the officially supported bridge from PX4 to. So we have actually replaced, particularly in the open source case, the old micro-RTPS bridge. And it lives as this micro-DDS client running within PX4. And for those of you who are PX4 people, you can go and have a look there and see exactly how it is all set up. Beyond just now including it in PX4, Auterion, we have started using it in some initial test projects, and we'll continue expanding these test projects and the tests that we do as the broader project evolves to make this split. So it's always better when you have an example. So I'd like to describe one of these initial test examples we've been working on. And in this case, it's an obstacle avoidance feature that we've added. So to give a brief outline of the system in that case, once again, of course, we've got our microcontroller and the mission computer. The mission computer gets telemetry and vehicle status information and any other data it needs from PX4. And this is all supplied to an avoidance application, is what I'll call it. This avoidance application also gets information from a depth camera. So in this case, it's a RealSense stereo camera, which observes the environment and can provide us with depth images which describe the environment our vehicle is flying through. And so in the ROS side, this high-level mode, essentially our avoidance application, makes use of the data from PX4 and from the depth camera to decide on some kind of constraint to the controller running on board PX4 to say, you might be wanting to go forwards, but there's something here in the way, you better stop or at least veer off a little bit to the side. And so here we have used and switched over to micro-XRCE-DDS as this bridge between the two, and we're evaluating its performance with this avoidance application. And so just to give you a brief taste of what it actually looks like when we're flying, here you'll see a video of myself and a colleague out testing this particular feature. We've got our drone hovering to start, and then we tell it to fly a mission. This mission happens to take it directly into the tree, which you see is in front of it right now. And after a few crossed fingers, you'll see that the drone does indeed stop. And we had no latency issues between these two devices. So here we go. Let's hope this plays for us. There we go.
Continue mission.
Great. As with these kinds of things, it's often not too much to see, but actually the value gained by something like that, your drone not crashing into the tree and you lose your drone and any data you've collected, the value gained is huge, and we're really pleased with the outcome. And in general, the way this integration with our new middleware is going, we're really excited about the next steps for it, especially after these initial successes. So speaking of next steps, what is next? Well, we've shown that the micro-XRCE-DDS bridge, it works. We can get the data between the two. But of course, in our broader switch to that new architecture, there are a few things missing. We need to continue developing and designing that commander, as well as that mode and control API. In this case, we've got multiple stakeholders and use cases to consider, so there's certainly more work to be done there, but it is ongoing. And finally, we do want to consider and keep doing more widespread testing of micro-XRCE-DDS in the new system, see if we can really push the limits of what it's capable of, having multiple apps or modes communicating at the same time. And so we'll continue to try this out and see how it goes. But for now, that's all from me. Thanks very much for your time. It's been good to share this with you. Of course, if you have any questions, please feel free to reach out. And perhaps we can start with the first one we had already a few minutes ago.
Yes, I think
so
Tomoya had a question.
Yes. So Tomoya, let me start with your first one.
Yeah, that was a question.
Oh, you want to ask? Go ahead.
Yeah, so you mentioned Android, right? So it sounds to me like a completely like a application framework, so that we can develop the application that can be running any platform supported Auterion. Is that the question is that like Auterion is conceal the platform?
As in saying that the platform that we developed, that is concealed and you can only plug something in on top? Is that what you're asking?
Yeah, so do you have like many platforms that we can run that specific application, any devices? So for me, so using the Auterion SDK and I developed the application, right? So that application should be running any Auterion platform. Is my understanding correct?
Right. Yeah. So if it's been developed for that particular system, of course, some work might be needed to make sure it runs exactly in our architecture, whatever the interfaces need to be. But yes, so certainly if it's been developed and you find it should be working, we think there should certainly be a way to get it all together. Yeah.
Okay. Thank you.
Yeah.
Yeah. Actually, I got a second question. So you guys use the XRCE-DDS, right? Instead of micro-ROS. So if you have any like insights or experience why you're not using a micro-ROS between the flight control and the mission computer, so if you can, would you like share your experience why using XRCE-DDS, not micro-ROS?
Right. So I think there's a bit more to it. It's not actually necessarily instead of micro-ROS. So micro-XRCE-DDS, I would call, say, the underlying bridge, and certainly on PX4 on the flight controller side, that is the straight micro-XRCE-DDS client. On the other side, on the mission computer side, you actually have a choice. You've got a choice of the micro-XRCE-DDS agent, which is just with that, but you can actually also use micro-ROS and have the micro-ROS agent running there to use that functionality on the other side. So it's not necessarily a one or the other. In fact, you can use both. I think our choice was or driven largely by the fact that at this point we wanted to essentially use the minimum solution required, which in this case is simply just the agent on that side. But it doesn't exclude you from using micro-ROS as well as if you want the added functionalities. And indeed, we have actually tried that out, and it has a lot of value there.
Okay, thank you very much.
Sure. Georgios, go ahead.
Yeah. Hi. Thank you for the presentation, Daniel. I have 2 or 3 questions. The first one is quite similar to the aforementioned one. Like, since you are using Linux in the bottom layer, I guess you are using like an application ARM, right? A Cortex-A.
Yes. Off the top of my head, I don't have the exact numbers. So
my question, if it is in this class of microprocessor which is quite powerful, why didn't you choose to just run ROS and simplify things? Like if, for example, you are using Yocto in the Linux environment, why didn't you directly use ROS and be able to use packages from ROS on the end?
Sorry, is this on the, maybe I'm misunderstanding you, on the flight controller?
Yes.
The FMU?
Yes.
Okay. No, sorry, then I told you the wrong thing. we use Linux on the mission computer side, but not on the flight controller. So the flight controller is the microcontroller that runs not Linux, but rather NutX. That is, compared to the mission computer, it is significantly more resource constrained over there. Yes, apologies for the misunderstanding.
Okay. And how easy was the integration with the TCP/IP stack that you use in your microcontroller with micro-DDS?
I'd say in the end, it went fairly smoothly. We didn't have too many significant challenges on that side. I think there were a few teething problems. We had to ensure Ethernet configurations were all correct, particularly because we have many other Ethernet devices that want to communicate on board and with our system. But we were able to sort of work through that with relative ease, and so it does work rather well. Yeah.
Okay. And my last question: how did you solve the state sync issue? Like, do you have your own custom mechanism to solve?
So that is actually one of the things that's still on the to-do. So what we've more been focusing on now is the message transparency. That's to do with, say, ROS messages, and on PX4 we have a different publish-subscribe architecture called micro-orb or micro-orb. So we've actually focused now in these initial tests rather on the message transparency. The state transparency is part of that future work as part of that broader split. Yeah. So that is something we're actually still thinking about, still working out. Yeah.
Okay. Thank you.
Sure.
So
Kimberly, I see you have a raised hand.
Next. Yeah.
Yes. Can you hear me? Oh,
yes.
Great. Yeah, let's see. I've written it down in the chat, but I can say it, of course. You probably brushed over it already in your presentation, but I think I missed a little bit. But I just wanted to know, which would you say are the biggest benefits to use micro-ROS over MAV link? And perhaps, is there anything that you miss from the MAV link?
Interesting. So I think one of the key things is that Mavlink has a number of sort of historical issues with it. It's how do I describe this? It's grown and evolved as the open source project has, and not necessarily always in the best way. It's got a lot of baggage and a lot of components that all need to work together, and very often they might fall apart. It can also have some sort of what's the word I want to use? Sort of resource overuse issues. So, example, we found Mavlink and some of the components around it can really sort of clog up the communication protocols on board our devices, and so we continue to have these frustrations with Mavlink because of this historical baggage, I think, largely. Also, one of the things with Mavlink is these message types are sort of quite predefined. And it's not so easy to simply extend the messages with a new one if you just want to quickly make another one. And you have to have all introduce the sort of translation between Mavlink and what's running on PX4. You have to do all of that in addition to what you have. When you switch to micro-ROS, you've got ROS messages and things like that, which are much easier to do the translation for. Everyone, as I've said, everyone kind of knows how to use ROS and ROS messages, and the infrastructure is just better built around that in that sense. So I think those are some of the key reasons. Anything we miss, I guess, what is nice about Mavlink is that it really is built for this specific use case. So you can include in Mavlink very specific commands, which are only useful in the case of an aerial vehicle, such as a takeoff command or a land now command, which ROS doesn't have by default, and you'd have to sort of integrate that in a different way by a certain command, which then commands you to go down. It's a bit more complex, whereas in Mavlink you can just say land. So that's quite nice to have, but it's not enough to make us keep it going. Yes.
All right. Yeah, thanks a lot. That's very clear to me. So I think at least we work with the small drone, the Crazyfly, and I think that's originally the reason why they haven't moved, they haven't tried Mavlink was because of the overhead, and also because of not being able to dynamically change the messages indeed. So
Yeah.
They wrote something by itself, but I've been they're slowly talked to move towards micro-ROS itself, and I think your experience is helping at least seeing some of the benefits of that. So yeah, thanks a lot.
Yeah. Sure.
Okay, and the last question, because we are a little bit late, is from Elliot, and he wants to know how the Auterion and ROS2 SDKs related in the context of this architecture, and if are they used side by side, or is one being reworked to be implemented on the top of other?
Sure. So I'd say at the moment, we'd say it's essentially that the Auterion SDK, or rather, the way we set things up, that is being adapted to try be more sort of ROS-friendly, ROS-based. So I'd say it's a bit of the latter, as you've suggested. So within Auterion and more broadly in PX4, I think what we're trying to say, ROS2 appears to be the way people are going in terms of industrial robotics. It's becoming more widely used, and so we want Auterion and PX4 to be open to that and compatible with that. So we'll be trying to adapt what we do to rather fit in with ROS2. We're not actively going and approaching, say, ROS2 and from the other side and say, hey, can we adapt to PX4 and Auterion? So I hope that answers your question.
Mm-hmm. So thank you very much. Okay, now we are going to see how an autonomous restaurant is working, isn't it, Tom?
Yep. Let me just get this started now.
Go.
Okay, does everyone see the screen?
Perfect.
Yep.
Great. Okay, so I'm from Mezli, and who is Mezli? I guess I'll start us off with. We're a small team of engineers and cooks and chefs working to basically create a mechanism for just serving healthy food that is fresh and affordable. So especially in America, there's a high tendency to eat a lot of fast food, fast casual that isn't necessarily the most healthy. And generally, there's an association that with healthier food, there's a higher cost. So we've been trying to sort of work on a system to serve healthy food that is both fresh and affordable. And I guess we've made basically a giant vending machine. So I am from Massachusetts, east coast of the United States, and I originally studied mechanical engineering, but near the end of that discovered that I had a tendency for actually mechatronics and enjoying writing the software that controls the mechanical things. So for the past 7 years, I've been doing mostly a lot of C#, Python, SQL, OpenCV, PLCs, various robotics things. I was at a consulting company prior to this. But one of the things is I hadn't actually done real embedded development since university. So when coming to Mezli, we had a few requirements that we needed embedded devices for. So when I first joined, there was the sort of concept of how the mechanical system would work, but nothing was designed. There were definitely no electronics, no real software, but there were some systems we knew we needed embedded devices to help control. So it was very, very vague, the sort of requirements. And within a year, we needed to design, build, and deploy the first unit. So we knew we needed embedded devices. And because of sort of the vagueness of all the requirements, I really needed something that helped support modular development. So the requirements, only some requirements at any time were actually defined. So I needed to be able to define many things in isolation and sort of work to tie them together over time as more requirements came out. And then support for high-level languages, preferably Python or C#, based on my previous experience, sort of leveraging things I already knew. I wanted something with out-of-the-box support in a large community and ecosystem and quick to get started. So when I looked at a few different options, especially things that would integrate with embedded devices, like 0MQ, MQTT, some embedded proto, and ROS and micro-ROS. And I guess sort of going through each of these systems, ROS and micro-ROS sort of checked it off. And really the thing that convinced me to go with ROS and micro-ROS was the first day that I tried using micro-ROS. We had a test development board. I was able to get the micro-ROS system downloaded on it with the debugger running and actually using the whole LWIP micro-ROS agent communicating back and forth with it from my PC. And I hadn't done embedded development in 5 or 6 years. So sort of having something with the kind of documentation and support in place to get started right away, even though micro-ROS doesn't claim to be production ready, it really gave me confidence that if something's that well documented, and then the support for it or the functionality of it is likely to have, based on my experience, also reliability. So why do we end up with the STM32? So we, again, had very vague requirements. I'll go over some of the things we actually did with the embedded boards. But at the time, we only really knew a few things we would be controlling with it, but we had thrown out maybe a dozen ideas of the kinds of devices we might end up controlling with the embedded boards. So we needed something that was honestly overpowered for most of those concepts, but would allow us to sort of customize each board and deployment and have confidence that we had both the basically the compute power. We weren't trying to save costs necessarily on making sure it's the cheapest board for this sort of proof of concept we're developing. We needed an embedded board that would just work, even if it was maybe twice as expensive, $40 instead of $20. So we needed something that was micro-ROS compatible was a big thing for us. Again, I hadn't done something in 6 years, so setting up a embedded project from scratch by myself would have been quite the undertaking versus having the sort of framework to build up around micro-ROS and the whole setup environment that exists there. Persistent storage for setting IPs in various configurations. Our devices read from an SD card on boot up to know both the static IP and various parameters of who they should be talking to and certain of the behaviors, controlling relay boards, digital inputs. One of the nice things about the Olimex board too is it is in the Olimex ecosystem. So they have various attachment boards that you can just almost just plug and play over their connectors that use I2C. And the digital inputs being opto-isolated were pretty nice because it protected us from potentially frying things. We're moving quickly and sometimes miswiring things and having sort of more protection of not frying our main board and worst case destroying the mod IO board was pretty nice. Analog inputs and miscellaneous IO. We ended up implementing something called one-wire, which I'll go into more detail shortly. But those are sort of the requirements. We looked at a few of the other boards in different ecosystems, but this was the one that just had all the things we needed, and we just sort of went with this. For our actual deployment, this is a gross oversimplification, but in the bottom, you can sort of see some of the different nodes we had in the yellow. So controlling our ovens, lockers, monitoring our environment, those talking to the micro-ROS agent running in Docker containers, and the sort of link between those and the rest of our Python ROS2 nodes was the discovery server. We had several dozen Python nodes. We had a very modular development. So when actually starting all those up at once and it becoming an n-squared problem of the discovery of all of them finding each other, it was quite a heavy load on the CPU and took quite a long time. And having the discovery server as a centralized place for all these things to communicate to each other was fantastic. And using Docker as well just made the whole process so much easier to develop and deploy. I could set up different PCs in our testing lab and in production very quickly without having to install all of the requirements and making sure all the packages all link together, versus just having Docker containers can just install Docker, link them to where they should pull code from, and they just got up and running. Just sort of showing the networking on the device, in our machine. We had sort of a private network and public network. I'll go into this why this is also some useful tools we use for interacting with the embedded devices remotely through the control PC later. But with the private network, there are many devices that we do not want connected to the outside world. We don't want someone to be able to, for example, talking to our cameras and seeing what's going on inside the machine or trying to control any of our motors. But we also need to be talking to the outside world in order to get food orders, in order to communicate with the larger environment of the world as a whole. So we have a control PC with sort of two NICs. So one on the private network, one is on the public network, sort of acting as a bridge between those two environments, both controlling the actual mechanical system, as well as talking to the outside world and managing inventory and going through all the different controls that needed to occur. This is not actually what's running on one of the embedded devices. This is actually what's on one of the Python nodes. When I was first developing those, basically we're using state machines everywhere, but in Python it was very easy, just in a few lines, to make it output the actual state diagram with arrows. So this one is actually a bit old, but one I still had lying around, of one of our sort of more coordinating level systems. We broke out things very modularly, so all the embedded devices, they don't actually talk directly to each other. They might be responsible for an individual subsystem, and then we used Python for sort of managing the behavior of many of the different states due to ease of speed of development and deployability and things like that in my own experience. And for talking to databases, talking to the servers over different frameworks of GraphQL or various REST APIs. So I'll go into a few of the different subsystems we actually used micro-ROS for now. One of them was controlling our ovens. We sort of had the option of using ovens that were designed to be used in a more automated system, but they didn't have the functionality we wanted, versus using ovens designed for people actually interfacing with them that had all the functionality we wanted, but had no actual interface to control. So we got creative. We used the ovens that had the functions we needed and figured out how to control them afterwards, which led to some fun and interesting things. Lockers, we have sort of a fun locker pickup system in environment monitoring. Both the oven control and environment monitoring were very important because we did not want things to catch on fire and keep pumping electricity into it. We needed to sort of know what was going on in order to control the system and ensure we're outputting safe, high-quality food and not catching on fire. So the oven. Basically, this oven had an array of buttons on it, but one of the main things we had to interact with was a keyboard. You can think of it sort of like a, on your phone, keyboard type display of 3x4 grid of numbers and buttons. And the way they actually implement this, which is common with keyboards, is something called keyboard scanning. And basically, you have a matrix of outputs and inputs, and the device in the oven can scan through the outputs by pulling certain outputs low and then measuring the inputs. And when you press a button, you're connecting the outputs and the inputs for a specific pin. And with various pull up and pull down resistors, this sort of allows you to actually know which button is pressed. So this was just a video online that shows sort of the process of scanning through the outputs and going through the inputs. But how could we actually control this? There wasn't just a single button we can try to fake out. So we actually could, with the interrupts on the device, see when they were pulling the outputs low by tying it to an interrupt pin, and then based on some timing and with a little bit of fudge factors, know when to, on our board, pull one of the inputs low to trick the device into thinking we're pressing a specific button at the time. In the bottom right, you can see before we were using the Olimexes, a little prototype where we were messing with various configurations of how we were going to potentially do that. Some of the buttons weren't on keyboard, the sort of keyboard scanning array though, for example, the on-off. So for those, we just used some relays. We also wanted to monitor the temperature. There's thermocouples to make sure the oven is at the current temperature, doing what we expect. And in order to also make sure the oven is behaving as we expected, since again, it's not designed for automation, we're not getting feedback that we actually pressed the right button. We were monitoring the current of different components. So adding current monitors over different wires and tying those into inputs on our Olimex, so we can make sure that, oh, when we press this button, we expect a current spike here and to hold and sustain a large power draw. And that sort of helped make sure that things were going correctly and no fuses had blown or something along the likes of that. And one of our interns actually came up with an idea that we didn't implement, but we maybe will in the future, of actually tying the output buzzer of the oven into an interrupt pin so we can see the frequency of the beeps it makes when you press buttons as a confirmation for behavior, because they actually have different sequences depending on what you're doing, which we thought was quite clever, but we didn't need for our situation. The lockers, various sensors being... Go. While we were still developing the system, things weren't fully painted. But so we're detecting the weight of the bowl. We have a line break sensor as well as confirmation. And then the electrochromatic glass. The door close sensor, electromagnetic locks. And when developing this system, I think me and my coworker, we both studied mechanical engineering. So our team was very small. It was 4 engineers, 3 mechanical, and me doing all the software and electrical procurement, assembly, design. So I actually had very little time for even all the software development, which is why using a system like ROS and micro-ROS really helped accelerate my ability to deploy and test code quickly. But it sort of showed in a few ways with making some silly mistakes. So some of my previous experience, I normally think of large motors as source of inductance. It's sort of obvious in hindsight, but at the time we didn't really think about the fact that an electromagnetic lock is a big electromagnetic and therefore a huge inductor. So when we were controlling that through relays, we were getting some massive voltage spikes and getting some strange behavior on our boards. The debugger was going wild, some weird signals, and things just weren't behaving the way we expected. And we eventually found out that we were inducing very large voltage spikes, and surprisingly, nothing broke. From that, we did have some water damage, though, of during development, not sealing things appropriately and being in a refrigerated environment, and condensation resulted in the loss of a couple boards, unfortunately. And for the environment monitoring, this is an example of how having an overpowered board with lots of extra I/O pins that we didn't design for played out to our benefit. We need to monitor the temperature in various devices. For food quality, we have to keep all the food below 5 degrees Celsius with an intended goal of 3 degrees Celsius, so we have some buffer room there. We also want to monitor the temperature near the ovens, make sure none of our electronics or our electrical cabinets were getting too warm, and we needed to improve the ventilation of any subsystem. But for monitoring the temperature, what we ended up going with were these DB18S20 sensors that use a protocol called one wire. So basically, it's a single wire that, in addition to, you can actually have it parasitically draw power, but the signal consistency isn't as good. But it's a single communication wire for the master and the slave devices to talk to each other. And on the right here, you can see some of the different signals as we're developing this process. We found some code online, but there's some fudge factors sort of involved depending on the length of your system, the way the signals propagate, and the amount of time it takes for the pull-up resistors to pull up and down, resulted in us actually having to hook up to an oscilloscope and modify some of the parameters. So we're holding things above the 10 milliseconds we need in the 10 to 15 range, versus when we plugged in our sort of longer stretch of these cables, we're getting 8 microseconds. So there was some fudging there to go on, but this worked very well and has been extremely robust. We were a little concerned when we first tested it. We had some issues, but once we dialed in some of the offsets, the one wire worked great. For actually cabling of it, we used Ethernet cables. We weren't sure how to create a continuous run and tee off of that run with our thermocouple sensors. So we used some Ethernet cables Trying to wrap up quickly here, so just a couple minutes left. With these Y splitters, which help provide some shielding and convenient packaging. This is a complete tangent, but if anyone ever needs a VPN solution, I use Tailscale and it was fabulous. So we have the private network here, for example, communicating with the embedded devices and cameras, but from the office or from anywhere, I might need to access one of those remotely. And I could install a Tailscale router and sort of access anything on that network, but then disconnect that router and no one else has access. And if you ever need to use a VPN, I just recommend it. It was a tool I found extremely useful over the past year, but not at all related to ROS or micro-ROS, just useful. My overall experience, the setup was extremely easy and things just worked. There were lots of different embedded boards integrated that I could choose from. The integration with the ROS2 ecosystem was great, reliable and stable publishing of messages, except for when I was messing with some QS settings and messed up a few things for a day there and had some fun. There's only one issue I've had with micro-ROS devices, and sometimes a service for me was taking it would work for hours, and then one service request would take 20 to 30 seconds to trigger, where it would just have send message being spammed every 100 milliseconds until eventually the device does something. During that time, the device was successfully publishing messages and seemed happy. The fact that it eventually did do things and I implemented some higher level retries means that it didn't drastically impact the behavior of our system. So I haven't actually dug into that yet. But now that we've deployed and developed our system, I'm hoping to actually figure out what was going on there. It was likely a user configuration error on my side. Since I am not an embedded expert, I likely made some kind of mistake that I need to find somewhere. But that's the only negative experience I've had with the whole ecosystem so far, and it's likely self-imposed. And here's a little, as we ask questions, here's a little video of someone using our system and shows a little bit of how the food is made. We're intentionally hiding things. This is while we're still developing it, of certain mechanical systems and how things are actually working, but you can see a little bit of what's going on here. Any questions?
Very interesting, Tom. Very, very interesting. Amazing.
I think it was a rather additional use of micro-ROS compared to many of the normal uses being in a more real-time ecosystem or more embedded specific uses. But it worked for us and has been just great.
Great. Great. Okay, any question? Okay, so thank you very much, Tom, and Daniel also for the very interesting talks. And okay, we are going to finish. And next we are going to begin with the Artificial Intelligence Integration Working Group. So if you want to stay, all of you are invited. So I'm going to stop and then start the record. Okay, see you guys.